Good morning. The circuit on the board is for you to work on, to remind yourself, since we haven't seen each other for a few days and it's been a weird week. We're just going to remind ourselves what we learned the last time we met, which I can't even remember which day that was.
Monday.
Sure, Monday. So, remember this, and here we go. Simplify the circuit, take clusters of resistors that follow the rules, and collapse them into a single equivalent resistor, and do that as many times as you need to until you get to just one resistor and a battery. And then work it backwards to solve for the current through and voltage across each specific resistor in the original circuit. Ready, go. So, my solution to this works by simplifying the circuit and then by desimplifying it over time, right? So I'm going to start with this, and I'm going to recognize that my three resistors, 10, 15, and 5 on the right, are all in series with each other, right? And then the 10 and the 15 on the left are in parallel with each other. So I'm going to look at 1 over 10 plus 1 over 15 equals 1 over 6, so 6. And then the other side, 20 plus 15 plus 5 is 40. So I'm going to just rewrite this as a 6 and a 40 in parallel with each other. Are we okay with that? And then the 6 and the 40 are in parallel with each other. So 1 over 6 plus 1 over 40 equals 1 over 5.22. So 5.22 is my total resistance. We all okay with that? There's other ways of simplifying it. For example, you could have kept the 10 and the 15 separate, just done the 40, and then do the 40, the 15, and the 10, all three of them in parallel. That also gets you there. Just a different way of doing it. Now I go backwards. I say, okay, down here, 10 volts, 5.22 ohms. I can do 10 over 5.22 and get 1.92 amps. That's the total current pushed. Then I go back a step. It's not really a 5.22. It's actually a 6 and a 40. 6 and the 40 are in parallel, which means what stays the same with them? Volts. So if 10 volts is dropped across the 5.22, that means 10 volts is dropped across either of these. Right, 10 volts there, 10 volts there. 10 volts and 6 ohms, 10 volts and 40 ohms gives me current. V over R, V over R. So I get 1.67 and 0.25. Quick check, I add up these two currents, 1.67 plus 0.25, I get 1.92. So the current split, not evenly, but in such a way that there was all the current there still. Then I recognize it's not actually a 6 and a 40, it's actually three resistors. The 40 splits into 3 in series. The 6 splits into 2 in parallel. Let's start with the series. What stays the same in series? 0.25, right? So I get 0.25 amps through the right-hand set of resistors. So I've got 0.25 amps times 20 is 5 volts. 0.25 amps times 15 is 3 3/4 volts. And times 5 is 1.25 volts. Quick check. I say 5 plus 3.75 plus 1.25 is 10 volts. Makes sense. Then on the other side, the thing that I get is the voltage. So that's a 10 volt drop here, which is a 10 volt drop here, so 10 volts and 10 volts. And I say V over R, and V over R gives me 1 amp and 0.67 amps, 1.67 being the total amperage, which is what we have here. Makes sense. Yeah, when the 6 splits to the 10 and the 15, I keep the voltage the same because they're in parallel. When the 40 splits to 20, 15, and 5, I keep the current the same because they're in series. So this is one way of solving this. We're going to investigate another way of solving this. Make sure you have all the answers written down because you're going to want them later to cross-check your work when we learn our new method. But our new method has to do with this guy named Kirchhoff. Really cool dude. I don't remember if I mentioned, so I'll mention it to you. Kirchhoff did two things that became both of them known as Kirchhoff's laws. Two completely separate studies. This one, which represents how to study circuits, and his other set of laws, also known as Kirchhoff's laws, are what happens when you shine a star through a hot hydrogen gas cloud in outer space. Those are his sets of laws. And we don't call them his first set of laws and his second set of laws, because you usually know which one you're talking about in context. Not a lot of light bulb circuits flying around in hot hydrogen gas fields and vacuums in outer space. So you either are talking about circuits or about stellar hydrogen gas. Interstellar hydrogen gas, I should say. So we're not going to talk about, which is really a problem, but we're not going to talk about the spectral emission of hot hydrogen gas, which is a shame because that's cool. Like, it's really cool. But here we are in circuits. So let's talk about the circuit laws instead of the hot hydrogen gas spectrum emission laws. And we're going to recognize two things. I've been buying you time so you can write this all down so that you can listen to the thing that I say after I'm done. I'm not just telling random stories. Turns out I have a purpose for it. But the loop rule is a recognition, as it says in parentheses at the end, of conservation of energy. Just like when you're skiing, you cannot start at the bottom of a hill, go up a lift, go down a run, come back to the same lift, and be at a different elevation. You can't do that. That is a violation of conservation of energy. You can't gain energy, lose all of it, and have more than you started with. That's not allowed. So the loop rule recognizes that. The loop rule says, okay, if I just pick a spot in a circuit, that X right there, and go around in a circle and come back to the same spot, my delta V should be 0. In other words, I should be at the same potential that I was before. I can't come back around and have a different amount of energy on my loop around. That's not allowed. If you make a loop and you come back to the same place, you're in the same spot that you used to be, conservation of energy. The second rule, the junction rule, is conservation of charge. Just like with a water pipe. If you take a junction in a water pipe, you have a hose that goes to two hoses that split off in different directions, you cannot have a gallon per minute going into the hose at that junction and 2 gallons per minute coming out of the hose. That means you're creating water in the hose. And likewise, you can't do less. You can't take a gallon a second going in and have a half gallon per second going out. That means you're destroying water. You're just making matter disappear. You cannot violate conservation of matter, conservation of mass. You cannot violate conservation of charge either. If you have I1 going into a junction that splits two ways, the sum of those two ways must be the original. Must be. If you have an amp going in, you have to have an amp going out. The sum of them must be an amp. Because otherwise, that means you're either creating or destroying electrons, which the universe does not allow. The universe doesn't like it when you destroy matter and turn it into nothing. Not allowed. So these two rules, which seem arbitrary, are actually fundamentally conservation of mass, conservation of charge. And you can't mess with those. With these, we can do some magic. We're going to go back to our simple circuit. Do you remember our first complex circuit, which is just a short series in parallel with another 20? Do you remember this one? We did this one on Monday. We're going to use Kirchhoff's laws to do something with that. I'm going to say, hey, there's a junction right here that splits into two different ways. I've got I1 going in, I2 and I3 coming out. What do we know about all those? How would we write an equation that would express how these are related? I1 equals I2 plus I3. Yes? The current going in must be the current going out. That must be true. Then we're going to use the loop rule to set up another equation. Why am I setting up more than one equation? Because if I have 3 unknowns, how many total equations do I need to solve? 3. I've got 1. Let's find 2 more. I'm going to take a loop. I'm going to go up from the bottom left corner, around, down through the first 2 resistors and back. And I know that that loop rule must result in 0 change in voltage because of conservation of energy. So I'm going to write an equation. This is my equation. I'll explain what it means. The 10 means plus 10 volts. From here, I go up through the battery. That adds 10 volts. Then, when I go through the 14, I lose voltage. The amount of voltage I lose is equal to I2, whatever it is, times 14 ohms. I times R is voltage drop, right? And then I subtract another I2 times 6. That's my other voltage drop. So I've gone up 10, down I14, down I6, and I should be back where I started. So the difference between all of those should be 0. That's just conservation of energy. Yes? So I'm going to take a different loop, because I need another equation, because I only have 2 and 3 unknowns. I need another equation. Write down the equation for the blue loop. Write it down. Write down what would you write that indicates the conservation of energy of an electron in the blue loop as it goes up and down its voltage path. Just quickly jot it down. It's not difficult. Use the green one as a template. So every time you go through a resistor, subtract that amount of voltage by doing I times R. What's my equation? Plus 10 minus 20 I3. Right, 10 volts up, 20 I3 volts down, and that should give me 0, a change of 0 because I'm back where I started, the loop rule. Now I've got 3 equations, 3 unknowns, so I can start solving. I can combine like terms on my green equation. I can say 14 and 6 both have I2, both are coefficients of I2, so I can add them together, combine like terms, and get 20. Add 20 to the other side, so it's 20 I2 equals 10. Divide by 20, that's a half. Yes? Same thing down there. I have minus I3 times 20. I'll add it to the other side, divide by 20. That's also a half. Half amp each way, which we already knew because it's 20 ohms and 20 ohms. Just one split into a series. And then with the 2 half amps, I do I2 plus I3 equals I1. That's half plus a half is 1 amp. And I just solved for the current in every branch. And now I can get the voltage anywhere I want. If I want the voltage of the 6 ohm resistor, I just say, well, that's I2. I2 is a half amp times 6 ohms, 3 volts. I've just solved for everything in the circuit without simplifying it by using the loop rule and the junction rule and setting up a system of equations. Fun fact, if you happen to know how to do it, you can set up a matrix. So I'm going to show you how to do that. We're going to imagine matrix headers of I1, I2, I3, and equals. Those are my matrix headers. And then I'm just going to put the coefficients of each of those as a matrix. So the first one is I1 equals I2 plus I3. So I'm going to say I1 minus I2 minus I3 equals 0. I'm just using the coefficients, right? If I1 plus I2 plus I1 equals I2 plus I3, I want to put all the i's on one side. So that's going to be I1 minus I2 minus I3 equals 0. So I1, 1 I1 minus 1 I2 minus 1 I3 equals 0. Do you see how I made that row in my matrix? Then the next one says that, let's see if I remember correctly, it was, well, 10 is on the equals side, right? So that's going to go here. 10 equals, and if I'm not mistaken, it was 20 I2, right?
Yeah.
And then the rest are zeros. And then the other one was 20 I3, so it was 0, 0, 20 equals 10. And that's my matrix. Now, I'm not actually entering this one, so that row is not actually there. You're just imagining that as being true. So when you throw this into your calculator, you're making a matrix. 1 minus 1 minus 1, 0, 0, 20, 0, 10, 0, 0, 20, 10. And you know that the first column is I1, the second column is I2, the second column is I3, and so on. And then if you know how to turn this into reduced row echelon form, you turn it into reduced row echelon form, and it will give you a matrix that will give you the solutions. So if you turn that into reduced row echelon form, you're going to get 1, 0, 0. Let's see, what was I1 again? Oh, just 1 amp. 1. Yeah. And then 0, 1, 0, 0.5, and 0, 0, 1.5. That's going to be your matrix, where 1 is I1, that's 1. 0, 1, that's I2 is 0.5. 0, 0, 1, that's I3 is 0.5. It'll give you a nice, clean solution.
Are they always 3 by 4?
No. This one is. The other ones are more complicated. Like the next one we do, we'll have 5 currents, which means it'll be 6 by 5. But you can always do this and get reduced row echelon form and be good. If you don't know what I'm talking about, feel free to ignore all this and just do it the way I taught you with substitution and elimination. But if you do, and you use reduced row echelon form, you win. Question?
Could you make it like, could you make it like I1 equals -1 and I2 is positive?
Yes. If you end up doing it the other way, that would also be fine. And the same way, if this was a negative, that could be negative as well. Like, it doesn't matter. As long as you solved it correctly, it'll turn out well for you. Now, here is my warning to you. Be careful with this. If you use reduced row echelon form to solve a system of equations, you must, 1, set up your equations correctly, and 2, enter it into your matrix correctly. If you don't, you will get an answer. It just won't be the right one. And that is important. Because on a test, like the way you tell me that you did this is you just write me a note that said, I used reduced row echelon form on my calculator, and then you just tell me the answers. If you're right, you win. If you're wrong, you don't win. Right? This is an all or nothing solution. If you try and do matrix math with this, and you get the wrong answers, you're going to lose pretty much all the credit. It's hard to find partial credit. So my suggestion is, do not let the first time you do this be on the exam. Do this many times. Every solution, solve it with Kirchhoff. If you're planning on using reduced row echelon form of a matrix, practice it like a dozen times and make sure you get it right every time before you just walk into the test, because you'll lose all the credit on a problem like this if you do it wrong. So just that's a warning to you. It's there for you to use. I want you to be aware of it, but you have to do it right, because it's hard to find partial credit when you just throw everything in your calculator and tell me the answers. I can't see where you went wrong. I don't know if it was a keystroke entry or a math problem, or if you set up your Kirchhoff equations incorrectly. I don't know, because I didn't see. It's hard to find partial credit. Yes?
So, would we get partial credit if we wrote down the equations in our matrix?
Show me as much work as possible.
Okay.
And depending on how I'm scoring the problem, you might get some partial credit. But like if you're here and you know, I don't know, you make this a minus instead of a plus because you miss a negative sign, but you use it correctly everywhere else, you might miss 1 out of 5 points.
Okay.
But if you throw it in your matrix as a negative, and I don't know that that's what you did, and you didn't write it down, and you're going to get everything wrong, you just lose all your points. You would get 0 out of 5, maybe 1 out of 5, depending on how you wrote it down. So just be careful with it. Know what you're doing, but it is a super elegant way of solving systems that I really like. Do this again, but use Kirchhoff's laws instead of circuit simplification. The nice one here is that you have the answers already. You know what the answers are because you solved them earlier today. So just with those answers, see if you can get them again using Kirchhoff's laws instead of circuit simplification. Ready, go. Hang on, I did forget. I wanted to set up the two junction rules for you, just to show you how you do it. What we're going to do is we're going to start with I1 always as being out of the battery. Always, 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 always. And then what happens? It hits a junction, and how does it split?
Right and left.
Right, left, I2, and I3. Are we done? No. There's another junction that we care about. Where is it? On the left-hand side, the 10 and the 15 split into I4 and I5 at this junction here. Do you see that? Now, anything else, when the 4 and 5 come back together, what do they form in this wire here? I3 again. And then when these two come back together, what do they form? So we don't have to worry about that. But anytime you get new currents, you have to do a new set of junctions. So we're going to have two junction rule equations. What's the first one? I1 equals I2 plus I3. And the other junction equation is? I3 equals I4 plus I5. How many more equations do I need? 3 more to solve for 5 unknowns. So I'm going to do 3 different voltage loops. Now do the rest. So here I am. I'm going to set up a loop like this, which is going to be 10 volts minus 10I4 is 0. You with me there? I3, by the way, doesn't have a voltage drop with it. I3 is just a wire, no voltage drop, so I3 shouldn't show up anywhere else. Then I'm going to do this loop, same as the red, except it takes that little green detour, which is 10 minus I5 times 15. And then I'm going to take the purple loop, which is 10 minus I220 minus I215 minus I25. 3 separate voltage drops, right? So I've got these 5 equations. Feel free to matrix them if you want. I'm not going to go through again how to do that. If you want to learn, come see me. If you already know how, good for you. I'm just going to start looking at this and say, well, one of the things I can do is this. I just add I4 10, divide by 10. I4 must be 1 amp. I can do the same thing for the green equation. Just add 15 I5. So that's going to be 0.67. And then the purple equation, I'm going to add like terms. So that's 40 I2. Hey, adding like terms is an algebra thing we do, but how do we sum up a series set of resistors? We add like terms. 5 plus 15 plus 20 is 40. Oh, there it is. We're not doing anything different. We're doing the same physics. We're just doing it in a different way. but it's the same physics. That's the sum of the series circuit right there. We win. Okay, so 40 over 10 is 1/4. So those are my three. Then I say, okay, I know I4 and I5. That's 1 and 0.67. So there's my I3. And then if I know I2 and I3, I can get I1. And there are my solutions. Nice little system of equations. Yes? Okay, one more for practice.
Oh dear.
Yeah. There it is. Okay, above the hubbub of people leaving because I forgot and end 5 minutes early, we're just going to talk about this. We have I1 that splits three ways, I2, 3, 4. So my junction rule is going to be I1 equals I2 plus I3 plus I4. We'll take the top loop, which is 15 volts minus I2 times 7. The next loop, which is 15 volts minus I3 times 2. And the next loop, which is 15 volts up minus I4 times 12, and then again times 9, a double drop. When I add these all up, you'll see that we have three equations on the bottom, each with their own only unknown. So I can find the solution for each of those simply, and when I add them all up, I get 10.35 amps. And that is my solution. From there I can find voltage drops and anything else that I need.